When the Voyager 1 spacecraft crossed into interstellar space in 2012, humanity celebrated a historic milestone. After 35 years of continuous travel, this small probe had finally escaped the sun's protective bubble and entered the vast emptiness between stars. The achievement felt monumental, a sign that we were becoming an interstellar species. But here's the paradox that should give us pause. Voyager 1, traveling at roughly 17 kilometers per second, faster than any human-made object designed to leave the solar system, would need more than 70,000 years to reach Proxima Centauri, our nearest stellar neighbor, located just 4.2 light-years away. And it isn't even heading in that direction. If we sent a craft directly toward Proxima Centauri at Voyager's speed, the journey would outlast all of recorded human history many times over. The uncomfortable truth hiding beneath our optimism about space exploration is that the universe operates under constraints so severe, so fundamentally unforgiving, that they might represent not engineering challenges to overcome, but absolute boundaries to what's physically possible for biological creatures like us. This isn't a story about insufficient funding or inadequate technology. Those are solvable problems. This is about forces woven into the fabric of reality itself, constraints that emerge from the basic laws governing energy, matter, time, and life. What makes these limitations particularly insidious is that they're largely invisible in our everyday experience. We live on a planet where distances are trivial by cosmic standards, where gravity provides constant orientation, where radiation is filtered by a magnetic field and atmosphere, where food and water are continuously available, where we're surrounded by the familiar rhythms of day and night. Step outside this narrow environment, and nearly everything changes. The forces that shape interstellar travel aren't dramatic or obvious. They're subtle, cumulative, and absolutely ruthless over the timescales required to cross the gulf between stars. Consider something as simple as speed. We're accustomed to thinking of speed as a resource you can purchase with sufficient energy. Want to go faster? Apply more thrust. Build a bigger engine. This intuition works perfectly well in our terrestrial experience. A more powerful car engine produces higher speeds. A larger rocket generates greater velocity. The relationship feels linear and predictable. But this intuition, like so many others adapted to life on Earth's surface, breaks down completely when you approach the scales necessary for interstellar travel. The problem isn't just that space is big, though it certainly is. The problem is that the energy required to accelerate a mass grows in a way that becomes prohibitive long before you reach the speeds that would make interstellar travel practical. Let's ground this in actual numbers, because the abstraction hides the true severity of the constraint. Imagine we want to send a relatively small spacecraft, say, 10,000 kilograms, roughly the mass of the Hubble Space Telescope, to Proxima Centauri in a human lifetime, perhaps 40 years. That requires an average velocity of approximately 1/10 the speed of light, or 30,000 kilometers per second. This is nearly 2,000 times faster than Voyager 1. Using conventional rocket propulsion, even with the most efficient chemical reactions available, the amount of fuel required doesn't just increase proportionally with speed, it increases exponentially. The rocket equation, derived by Konstantin Tsiolkovsky in 1897, describes this relationship with mathematical precision. To achieve a given change in velocity, the ratio of initial mass to final mass must increase exponentially with that velocity change. For the speeds we're discussing, this ratio becomes absurd. Even using a perfectly efficient matter-antimatter reaction, which converts mass directly into energy with 100% efficiency, something we cannot currently do, the fuel required would exceed the mass of the spacecraft by factors of thousands or millions, depending on the exact velocity profile. You might think the solution is to accelerate slowly over a very long period, avoiding the tyranny of the rocket equation by using something like an ion drive, which provides tiny but continuous thrust. Ion drives have indeed revolutionized satellite propulsion within our solar system. They're efficient, reliable, and capable of producing substantial velocity changes over months or years. But the energy still has to come from somewhere. An ion drive doesn't violate physics. It simply uses electrical energy to accelerate ions rather than relying on chemical reactions. For interstellar velocities, the electrical power requirements become staggering. The kinetic energy of a 10,000 kilogram spacecraft moving at 1/10 light speed is approximately 4.5 times 10 to the 18th joules. That's roughly equal to the total energy consumption of the entire United States for about 3 years, all concentrated into accelerating a single small spacecraft. And this is just the kinetic energy of the final velocity, not accounting for inefficiencies in the propulsion system, which are always substantial in real devices. Some proposals attempt to sidestep this problem by leaving the power source behind. A laser sail, for instance, would use enormous laser arrays stationed near Earth or in solar orbit to push a lightweight reflective sail attached to a small probe. The power source remains stationary, so you're not accelerating its mass along with the spacecraft. This approach, championed by initiatives like Breakthrough Starshot, seems promising on paper, but the engineering challenges multiply when examined closely. To accelerate even a tiny probe, perhaps 1 gram, about the mass of a paperclip, to 1/5 light speed requires lasers with power outputs measured in gigawatts, sustained for minutes. The optics must remain perfectly aligned across millions of kilometers as the probe accelerates away. The sail material must withstand temperatures that would vaporize most substances while remaining thin and light enough to achieve the necessary mass ratio. And once the probe reaches its target velocity, there's no way to slow down. It will pass through the Proxima Centauri system in a matter of hours, recording data as it screams past at 60,000 kilometers per second, with no possibility of returning images until years later when the light-speed transmission finally reaches Earth. But let's assume, for the sake of argument, that we somehow solve these propulsion challenges. Suppose we develop a technology that can accelerate a crewed spacecraft to a meaningful fraction of light speed without requiring impossible amounts of energy or fuel. We're still confronted by a force that most people never consider when imagining interstellar journeys: radiation. Space is not empty. Between stars, there exists an incredibly diffuse medium of gas and dust, averaging perhaps 1 atom per cubic centimeter. This sounds like nothing, barely distinguishable from a perfect vacuum. But at relativistic speeds, even this tenuous material becomes lethal. When your spacecraft is moving at 10 or 20% of light speed, each collision with a hydrogen atom occurs with kinetic energy comparable to a particle in a high-energy physics experiment. The atoms strike the leading surface of your spacecraft with such force that they produce secondary radiation, generating showers of particles that can penetrate deep into the structure. The biological effects of this radiation exposure are not speculative. We have extensive data from both space missions and medical radiation therapy. High-energy particles damage DNA directly, breaking the molecular chains that encode genetic information. Cells have repair mechanisms for this damage, but those mechanisms can be overwhelmed by high doses or chronic exposure. The damage accumulates over time, increasing cancer risk, damaging the cardiovascular system, affecting cognitive function, and accelerating cellular aging. During a journey lasting decades, crew members would be exposed to radiation doses far exceeding anything experienced in human spaceflight history. Even with shielding, the energies involved make complete protection impossible without absurd amounts of mass. Thick layers of water or polyethylene can absorb or deflect some of the radiation, but adding shielding adds mass, which requires more energy for acceleration, which brings us back to the propulsion problem. Every engineering solution in interstellar travel seems to loop back to energy and mass constraints. The radiation from interstellar hydrogen atoms is only one component of the problem. There's also cosmic radiation, high-energy particles originating from supernovae, active galactic nuclei, and other violent astrophysical processes. These cosmic rays permeate the galaxy, and unlike the directional radiation from interstellar medium collisions, they come from all directions. Earth's magnetic field deflects most cosmic rays, and our atmosphere absorbs what gets through, so we're shielded from the worst effects. In interstellar space, there is no such protection. Astronauts on the International Space Station experience radiation doses roughly 10 times higher than people on Earth's surface, even though they're still within Earth's magnetosphere and only 400 kilometers above the ground. In deep space, beyond any planetary magnetic field, the exposure increases further. On a multi-decade interstellar journey, the cumulative dose would likely exceed levels considered survivable without extraordinary shielding measures. Some proposals suggest creating artificial magnetic fields around the spacecraft to deflect charged particles, mimicking Earth's magnetosphere. This approach has theoretical merit, but the engineering is daunting. Generating a magnetic field strong enough to provide meaningful deflection over a volume large enough to protect a crewed spacecraft requires superconducting magnets with enormous power requirements. The field would need to extend hundreds of meters in all directions to provide adequate shielding, and maintaining it for decades without interruption introduces reliability concerns that border on the absurd. A single failure in the magnetic shielding system during the interstellar cruise phase, when repairs might be impossible, could expose the crew to lethal radiation doses within days or weeks. Then there's the question of what the crew is doing during these decades in transit. This isn't like a long sea voyage, where at least you have the psychological anchors of weather, waves, the movement of sun and stars across the sky, the rhythms of day and night tied to Earth's rotation. In interstellar space, nothing changes. The stars are fixed points of light, so distant that their positions don't shift perceptibly even over years of travel. There are no planets, no moons, no asteroids passing by. The view from the window is identical today, tomorrow, 10 years from now. The sun behind you gradually dims as you travel farther away, but the change is so slow it's imperceptible from day to day. The destination star ahead gradually brightens, but again, the change is glacial. You're suspended in a featureless void, traveling at unimaginable speed while experiencing no sensation of motion whatsoever. The psychological research on isolation and confinement, while extensive, can only partially predict the effects of such an environment. Studies of Antarctic research stations, submarines, and long-duration spaceflight missions provide some data. We know that isolation produces measurable changes in mood, cognition, and social dynamics. Conflict becomes more likely. Depression and anxiety increase. Circadian rhythms can become disrupted without natural light cycles. Cognitive performance declines in some domains, but these studies involve durations measured in months, occasionally a year or two. An interstellar journey would last decades. No human has ever experienced anything approaching that duration in such extreme isolation. The longest single spaceflight in history is Valery Polyakov's 437 days aboard the Mir space station, and even that was punctuated by regular communication with Earth, supply ships arriving every few months, and the knowledge that return was possible at any time if something went catastrophically wrong. On an interstellar journey, there is no return. Once the spacecraft reaches a certain velocity, turning around requires just as much energy as continuing forward. You're committed, and communication with Earth, even if possible, becomes increasingly strained by distance. Radio signals travel at the speed of light, so a message sent from a spacecraft 1 light-year from Earth takes 1 year to arrive, and the response takes another year to return. 2 years for a single exchange. As the journey progresses and distance increases, this delay grows longer. Conversations become impossible. You can send reports, receive occasional updates from Earth, but the connection becomes attenuated and abstract. The people you left behind age, have children, die. By the time you're halfway to Proxima Centauri, everyone you knew before launch has likely passed away, assuming a 40-year transit time and that you were an adult when you left. You're traveling toward a destination that will take the rest of your life to reach, sustained by the hope that the next generation, or the generation after, will complete the mission you began. This brings us to one of the most profound unseen forces limiting interstellar travel: biology itself. Humans are not designed for the environment of space. Every system in our bodies evolved under the constant downward pull of Earth's gravity. Our cardiovascular system is optimized to pump blood upward against that pull. Our skeletal system is built to support our weight. Our vestibular system uses gravity to determine orientation. Remove gravity, and all these systems begin to fail in predictable ways. Bones lose density at roughly 1% per month in microgravity. Muscles atrophy without the constant resistance that gravity normally provides. The heart becomes deconditioned, losing mass and efficiency. Fluid shifts from the lower body to the upper body, causing facial puffiness and increased intracranial pressure. Vision can be affected by changes in the shape of the eyeball due to fluid redistribution. The immune system becomes less effective. Wound healing slows. Even the gut microbiome changes in ways that aren't fully understood. We've developed countermeasures for some of these effects. Astronauts on the International Space Station exercise several hours each day using specialized equipment that provides resistance to simulate the loads normally created by gravity. But these countermeasures are imperfect. Even with rigorous exercise, bone density continues to decline. Muscle mass can be partially maintained, but not at Earth normal levels. And the time scales we're discussing for interstellar travel dwarf anything we've tested in actual spaceflight. The longest any human has spent in microgravity is 14 months, achieved by cosmonaut Valery Polyakov during multiple missions. An interstellar journey would last decades. The cumulative effects over such durations are unknown because we've never subjected anyone to them. We can extrapolate from shorter missions, but biology is complex, and extrapolation becomes increasingly uncertain as you move beyond the tested range. One solution frequently proposed is to create artificial gravity by rotating the spacecraft. If the habitable section of the vessel spins, centrifugal acceleration can simulate the feeling of gravity, pressing the crew outward toward the hull. This approach is theoretically sound and avoids the biological problems of long-term microgravity, but it introduces its own engineering and physiological challenges. To generate Earth normal gravity without creating disorienting Coriolis effects, the sensation of forces acting on you when you move within a rotating reference frame, the habitat needs to be large. A rotating cylinder with a radius of just 10 meters, spinning fast enough to create 1 g of acceleration at the rim, would produce noticeable and unpleasant Coriolis forces when the crew moves their heads or walks. Increasing the radius reduces these effects, but increases the mass and structural complexity of the spacecraft. A comfortable rotating habitat might need a radius of 100 meters or more, which means the overall diameter of the structure exceeds 200 meters. Building something that large, strong enough to withstand the structural loads of continuous rotation for decades, and light enough to accelerate to interstellar velocities, is an engineering challenge of staggering proportions. There's also the problem of reliability. A spacecraft designed for a journey measured in decades must function without failure for that entire duration, or at least without failures that can't be repaired by the crew using available resources. This is not how we currently build machines. Satellites and space probes are designed with redundancy and, when possible, repairability, but they're also accepted to have finite lifespans. When a component fails on a Mars rover or an orbital telescope, we work around it or accept the loss of certain functions. On an interstellar journey, some failures would be catastrophic. A breach in the hull, a failure of the life support system, a malfunction in the propulsion or power generation that can't be repaired. Any of these could end the mission and kill everyone aboard. The reliability requirements are orders of magnitude beyond anything we've achieved in spaceflight. Every system must be designed with multiple layers of redundancy, with components that can last for decades without maintenance, or with the ability to manufacture replacement parts using onboard resources. This adds mass, complexity, and cost. The cost, incidentally, is not a minor consideration even in a discussion focused on physical constraints. While it's true that cost is a human limitation rather than a fundamental law of physics, the resources required for interstellar travel are so vast that they represent a practical barrier nearly as insurmountable as the physics itself. The energy requirements alone, as discussed earlier, are comparable to years of total energy production for an advanced industrial society. The materials, the manufacturing, the testing, the labor, all of this requires a sustained commitment of resources at a scale that would strain even a wealthy global civilization. And unlike other large-scale projects, there's no economic return. An interstellar mission can't mine resources and send them back, can't establish trade routes, can't generate profit. The only return is knowledge and the satisfaction of achievement, which are valuable but don't pay for the next mission. This creates a fundamental mismatch between the resource investment required and the tangible benefits that could justify it to a society. Let's turn to another unseen force: the sheer difficulty of navigation at interstellar distances. When we send spacecraft to Mars or Jupiter, we can track their positions with extraordinary precision using radio signals. We know where the planets will be years in advance because their orbits are well characterized and predictable. We can calculate trajectories that minimize fuel use by taking advantage of gravitational assists from intermediate bodies. But interstellar navigation is a different challenge altogether. Stars move relative to one another with velocities of tens of kilometers per second. Over the decades required for an interstellar journey, both the departure star, our Sun, and the destination star will have moved substantial distances. Proxima Centauri is moving at roughly 22 kilometers per second relative to our solar system. Over 40 years, that's a displacement of roughly 27 billion kilometers, or about 180 times the distance from Earth to the Sun. You can't aim at where Proxima Centauri is now, you have to aim at where it will be when you arrive, accounting for both its motion and your own. This seems like a solvable problem. Just calculate the predicted position and aim accordingly, but the calculation requires knowing your own velocity with extraordinary precision. At 1/10 light speed, an error of just 1 part in a million in your velocity translates to a positional error at arrival of trillions of kilometers. You missed the target star system entirely, passing it at a distance where you couldn't even meaningfully observe the planets, assuming there are any. Mid-course corrections are possible in principle, but they require carrying additional fuel or propellant, which brings us back to the mass and energy problem. Every kilogram of fuel you reserve for course corrections is a kilogram that increases the initial mass of the spacecraft, requiring more energy for the initial acceleration. And making course corrections at relativistic speeds is itself problematic because even small velocity changes require enormous amounts of energy when your mass is already traveling at a substantial fraction of light speed. Then there's the problem of deceleration. If your goal is not merely to fly past the destination at high speed but to actually enter orbit or land, you need to shed all that velocity you spent so much energy acquiring. Conventionally, this would require carrying fuel for a deceleration burn, roughly doubling the fuel requirements for the entire mission. Some proposals suggest using the destination star's magnetic field or solar wind to slow down, deploying a magnetic sail that interacts with charged particles streaming from the star. This is elegant in theory but has never been tested even in our own solar system, let alone at interstellar distances. Other concepts involve using the gravitational field of the destination star or its planets to shed velocity through a series of close passes. But this requires arriving at precisely the right angle and velocity to be captured rather than slingshot away, and the margin for error is vanishingly small. There's also the question of what you find when you arrive. Our observations of exoplanets, planets orbiting other stars, have revealed a stunning diversity of planetary systems. We've found hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, systems with planets in configurations wildly different from our solar system, planets with eccentric orbits that carry them from scorching heat to frozen cold over the course of a single year. Proxima Centauri does have at least one confirmed planet, Proxima Centauri b, discovered in 2016. It orbits within the star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. But Proxima Centauri is a red dwarf, a type of star that produces intense flares, sudden, violent outbursts of radiation and charged particles. These flares could strip away a planet's atmosphere over time, sterilize its surface with radiation, and make it utterly hostile to life. We don't know whether Proxima Centauri b has a magnetic field strong enough to protect it, whether it has an atmosphere at all, or whether it's tidally locked with one face permanently toward the star and the other in eternal darkness. You would be committing multiple generations and vast resources to reach a destination that might turn out to be completely uninhabitable. This uncertainty introduces a temporal paradox that's rarely discussed. Suppose we launch an interstellar mission today with the best technology currently available, a journey that will take, say, 1,000 years. Over the course of those 1,000 years, if civilization continues to develop, technology will almost certainly advance. At some point during that millennium, we might develop faster propulsion systems that allow a second mission to overtake the first. The crew of the original mission, if they're even still conscious and not in some form of suspended animation, would arrive at the destination only to find that later missions launched centuries after them have already been there for decades or even centuries, having traveled the same distance in a fraction of the time. This scenario seems absurd, but it's a logical consequence of sustained technological progress over timescales relevant to interstellar travel with current or near-term technology. It creates a disincentive to launch missions at all, since waiting a few more decades or centuries might yield technology that makes the journey vastly more feasible. Suspended animation or cryogenic preservation is often proposed as a solution to the biological and psychological challenges of long-duration spaceflight. If the crew could be safely frozen or placed in a state of metabolic stasis, they wouldn't age, wouldn't experience the psychological toll of decades in isolation, wouldn't require life support consumables like food and water for the entire journey. But this technology, despite being a staple of science fiction, does not exist. We can slow metabolism in some organisms under carefully controlled conditions. Some animals naturally enter states of hibernation or torpor where their metabolic rate drops dramatically. Small organisms like tardigrades can survive being frozen or desiccated, but preserving a human in a state from which they can be revived after decades is far beyond current medical capability. The problem isn't merely that we haven't figured out the right technique. The problem is that ice crystals form inside cells when tissue freezes, rupturing cell membranes and destroying cellular structures. Various cryoprotectant chemicals can reduce this damage, but none eliminate it entirely, and the toxicity of the chemicals themselves becomes problematic at the concentrations needed to prevent freezing damage. Some research focuses on vitrification, turning tissue into a glass-like solid without forming ice crystals. But achieving this uniformly throughout an entire human body without damage remains an unsolved problem. And even if we could successfully preserve someone, we need to keep them preserved reliably for decades, maintaining precise temperature control and ensuring no degradation occurs. Then we need to reverse the process, warming and reviving them without causing additional damage. Each of these steps involves failure modes that could be fatal, and we have no way to test the complete cycle over the relevant timescales without actually freezing someone for decades, which is not something we can ethically or practically do. Another biological limit that's often overlooked is the question of reproduction and generational turnover. If a journey lasts longer than a human lifetime, the crew that arrives will not be the same people who departed. Children would be born, raised, and spend their entire lives aboard the spacecraft, knowing Earth only through recordings and stories. This introduces profound ethical questions. Is it acceptable to create people whose entire existence is confined to a spacecraft, who never experience the feeling of wind, the sight of a natural horizon, the sensation of rain, who never have the choice to leave or pursue a different life? These aren't hypothetical questions. They're considerations that would need to be addressed in any multi-generational mission design. The children born aboard the ship are not volunteers. They didn't choose to participate in the mission, yet their entire lives would be shaped by a decision made generations earlier by people they never met. The social dynamics of a multi-generational crew are also unpredictable. How do you maintain cultural continuity and mission focus over multiple generations? How do you prevent the formation of factions or conflicts that could jeopardize the mission? How do you ensure that the fifth or sixth generation still cares about completing a mission that was initiated by their distant ancestors? There's a real risk that, over time, the mission itself becomes less important than immediate concerns, interpersonal relationships, governance of the small community aboard the ship, the daily challenges of maintaining life support, and managing limited resources. The original goal of reaching another star system might fade into abstract mythology, something talked about but not genuinely believed or prioritized. We have some historical parallels in isolated human communities, but none that perfectly match the conditions of a spacecraft where return is impossible and the environment is entirely artificial and dependent on functioning technology. There's also the matter of genetic diversity. A small founding population, even one carefully selected for genetic diversity, will experience genetic drift and potential inbreeding over multiple generations. To maintain a healthy population without significant inbreeding, you need a founding population of at least several hundred individuals, possibly more depending on how long the journey lasts and how many generations are expected before arrival. This dramatically increases the size and complexity of the spacecraft, the amount of life support consumables required, and the energy needed for acceleration. Let's consider the energy problem from another angle. All human activity, including life itself, requires energy. On Earth, we have an essentially limitless energy source. The sun delivers roughly 1 kilowatt of power per square meter of surface area during daylight hours. Plants capture this energy through photosynthesis, and that captured energy flows through ecosystems, sustaining all life on the planet. On a spacecraft traveling between stars, solar energy becomes unavailable once you're far enough from the sun's solar panels become useless in deep space. You need an onboard energy source that can function reliably for decades without refueling. The only technologies we currently have that even approach this requirement are nuclear reactors and possibly fusion reactors if we ever develop practical ones. Nuclear fission reactors can indeed operate for decades, as demonstrated by naval submarines and some space probes like Voyager, which carry radioisotope thermoelectric generators. But scaling up to provide enough power for a crewed spacecraft is non-trivial. A crewed habitat requires substantial power for life support, lighting, temperature control, equipment operation, and recycling systems. The reactor must be shielded to protect the crew from radiation, and that shielding adds mass. The reactor also generates waste heat that must be dissipated, and in the vacuum of space, the only way to dissipate heat is through thermal radiation, which requires large radiator panels. These panels add more mass and complexity. Every kilogram added to the spacecraft requires more energy for acceleration, and we're back to the fundamental energy-mass constraint that pervades every aspect of interstellar mission design. Fusion power, if it becomes practical, might offer better energy density, and lower mass for a given power output compared to fission. But we've been working on controlled fusion for over 70 years and still haven't achieved a reactor that produces more energy than it consumes, let alone one that could operate reliably on a spacecraft for decades. Even if we solve the scientific and engineering challenges of fusion power on Earth, adapting it to the space environment introduces additional complications. The magnetic confinement systems used in most fusion reactor designs require superconducting magnets, cryogenic cooling, and precise control systems, all of which must function flawlessly for the duration of the mission. Another subtle constraint is information. We often think of information as weightless and costless, but transmitting information across interstellar distances requires energy, and receiving it requires a detectable signal. The strength of a radio signal decreases with the square of the distance from the source. A signal transmitted from Proxima Centauri would be extraordinarily weak by the time it reaches Earth, spread out over a sphere with a radius of 4.2 light-years. Detecting such a signal requires large, sensitive receivers and careful filtering to distinguish the signal from background noise. Transmitting a signal strong enough to be received requires substantial power. If a spacecraft at Proxima Centauri wants to send high-resolution images back to Earth, it needs a powerful transmitter and a large antenna to focus the signal toward Earth. This equipment adds mass and requires energy, which must come from the onboard reactor. There's a fundamental trade-off between data rate, transmission power, and antenna size. You can't send back high-definition video on a tiny, low-power transmitter, and even with optimal equipment, the transmission time is at least 4.2 years because the signal travels at the speed of light. There's also the problem of what I'd call existential sustainability. Spacecraft systems degrade over time. Materials become brittle from radiation exposure. Mechanical parts experience wear. Electronic components fail. On Earth, we address this through manufacturing infrastructure that can produce replacement parts. On a spacecraft, you're limited to whatever resources you brought with you or can recycle from existing materials. You might carry spare parts for critical systems, but you can't carry spares for everything. And you certainly can't carry a full manufacturing facility capable of producing complex electronics or precision mechanical components from raw materials. Some proposals include 3D printing or other manufacturing technologies, but these still require raw material feedstocks and can only produce items within the capabilities of the equipment. You can't 3D print a computer processor or a high-precision gyroscope with current technology. Some failures might simply be unrecoverable, ending the mission or leaving the crew with degraded capabilities. I want to return to the radiation problem because it's often underestimated in popular discussions of space travel. We've talked about cosmic rays and the interstellar medium, but there's another radiation source that becomes relevant at high velocities: the cosmic microwave background. This is the faint afterglow of the Big Bang, radiation that fills all of space with a nearly uniform temperature of about 2.7 Kelvin. At rest relative to this radiation, it's harmless. But if you're moving at a substantial fraction of light speed, relativistic effects cause the radiation to become blue-shifted in the forward direction. The gentle microwave background becomes higher-energy radiation, potentially ultraviolet, or even X-rays in the direction you're traveling. This creates an additional radiation exposure that scales with velocity. The faster you go, the worse it gets. At a high enough fraction of light speed, perhaps 30 or 40%, the blue-shifted cosmic microwave background alone could deliver a lethal radiation dose to unshielded crew members over the course of the journey. This is a fundamental physics limitation that can't be engineered away without massive shielding, which brings us back to mass and energy constraints. There's also a thermodynamic consideration that's rarely mentioned. Spacecraft generate waste heat from all their systems: crew metabolism, electrical equipment, nuclear reactors, computers, lights. This heat must be radiated away to prevent the interior from overheating. On Earth, we have convection and conduction to move heat around, and the atmosphere absorbs and radiates heat. In space, there's no atmosphere and no convection. Heat can only be radiated away from the surface of the spacecraft, and the rate at which you can radiate heat depends on the surface area and the temperature difference between the spacecraft and the surrounding space. A larger surface area radiates more heat, but it also adds mass and increases the cross-section for impacts with interstellar material. There's an optimal size for thermal management, and that size constrains how much power you can safely generate and use aboard the spacecraft. If you generate more heat than you can radiate, temperatures inside the habitat will rise until you reach a new equilibrium, which might be uncomfortably hot or even dangerous for the crew and equipment. Now, consider the psychological dimension of time perception. Humans evolved with certain time horizons. We plan for the future in terms of years or decades. We remember the past across a similar span. The longest-lived humans reach roughly 100 years. Our sense of purpose and meaning is often tied to goals we can expect to see completed within our lifetime. An interstellar mission lasting decades, or centuries if we're considering slower travel, exceeds these natural time horizons. How does a person maintain motivation and purpose when the goal is something they will never personally experience? When the destination is so far away that even traveling at an appreciable fraction of light speed, it remains decades distant? This isn't a technical problem with a technical solution. It's a deep psychological challenge that intersects with questions of meaning, identity, and what makes a life worth living. If you enjoy seeing the real forces that shape the future of space exploration, interacting with this video makes it more likely you'll discover similar content, almost like a hidden reward for curiosity. I want to emphasize something crucial. None of these limitations mean interstellar travel is absolutely impossible. Physics doesn't forbid it. The laws of thermodynamics and relativity permit spacecraft to travel between stars, but they impose such severe constraints that the gap between what's theoretically possible and what's practically achievable with foreseeable technology is vast. We can send small, unmanned probes on one-way trips, and we likely will within the next century. Projects like Breakthrough Starshot represent serious attempts to do exactly that. But crewed missions where humans travel to another star system and potentially return or establish a settlement, face constraints that are orders of magnitude more severe than anything we've encountered in space exploration to date. Each constraint compounds the others. The energy problem makes it difficult to achieve high velocities. Low velocities mean long journey times. Long journey times exacerbate the biological problems of extended microgravity and radiation exposure. They also strain the limits of mechanical reliability and crew psychology. Attempts to solve one problem, for instance, creating artificial gravity through rotation, create new problems in structural engineering and mass budgets. Attempts to solve the reliability problem by carrying spare parts and manufacturing equipment add mass, which requires more energy for acceleration. There's no single bottleneck that, once solved, makes interstellar travel straightforward. Instead, there are dozens of interrelated constraints, each severe on its own, and solving all of them simultaneously with a design that's actually buildable and affordable is a challenge that may genuinely be beyond our capabilities for a very long time, possibly indefinitely for biological crews. This brings us to an uncomfortable possibility, that the universe, by its fundamental structure, is not easily traversable for creatures like us. The distances are too vast, the energy is too great, the timescales too long, the environment's too hostile. We exist in a narrow band of conditions: moderate gravity, filtered radiation, abundant energy from a stable star, liquid water, breathable atmosphere, comfortable temperatures, magnetic field protection, a food web to sustain us. Step outside these conditions, and survival becomes difficult or impossible without extensive technological support. That technological support requires energy, materials, reliability, and capabilities that scale with the duration and distance of the mission. For journeys within our solar system, we can manage this. We can build spacecraft that support humans for months or a few years. We can resupply them. We can bring them back. But interstellar distances represent a qualitative change, not just a quantitative one. It's not simply that the journey is longer. It's that the journey is so much longer that entirely new categories of problems emerge, and the solutions to those problems strain or exceed the limits of what's physically and practically possible. Imagine the timeline of human technological development. Powered flight was achieved in 1903. 66 years later, humans walked on the moon. The pace of progress is astonishing, driven by intense competition, massive investment, and the convergence of advances in materials, electronics, propulsion, and computation. It's tempting to assume that interstellar travel is just a matter of decades or centuries, but the challenges of traveling to other stars are not merely bigger versions of the challenges of reaching the moon. Lunar missions required large rockets, precise guidance, and a journey lasting days with near-instant communication with Earth, and the ability to abort at almost any stage. Interstellar travel demands entirely new solutions, energy generation and storage at scales beyond our current capabilities, propulsion systems operating thousands of times faster than today's spacecraft, habitats that can sustain human life independently for decades or centuries, shielding from lethal radiation doses over long times, and maintaining psychological health and social cohesion in extreme isolation. These are not incremental improvements. They are paradigm shifts that may require physics and engineering principles we haven't yet discovered. Some imagine generation ships, massive, self-sustaining habitats where multiple human generations live and die during the journey. While fascinating as thought experiments, the practical challenges are staggering. You're not just building a spacecraft. You're building a fully closed ecosystem that must function longer than any civilization on Earth has existed. Everything, air, water, food, waste, governance, knowledge preservation, must be maintained perfectly. Any failure, a crop blight, a mechanical breakdown, or social collapse, could doom the mission. Humanity struggles to build structures lasting centuries. Machines functioning independently for centuries are unheard of. Yet a generation ship would need exactly that in an environment far harsher than Earth. Then there's the question of usefulness. Knowledge gained from interstellar missions is compelling. New life, physics, or resources. But information takes years to return at light speed. A probe at Proxima Centauri reporting discoveries would take 4.2 years to reach Earth. Follow-up instructions take another 4.2 years. Physical resources from other star systems cannot be returned. Energy costs make that impractical. The benefits are knowledge and achievement alone. This raises the philosophical question: why undertake such missions? Motivations vary. Some argue for exploration and expanding human experience. Others argue for survival, ensuring humanity becomes a multi-star species to hedge against existential risks. While compelling, these reasons are insufficient to justify enormous sacrifices unless humanity prioritizes them over pressing earthly challenges like poverty, disease, and environmental crises. The constraints on interstellar travel are not purely technical. They are deeply human. They involve values, perceptions of time and legacy, willingness to accept risk, and readiness to commit resources across generations. Even if technology existed, a civilization unwilling to accept these challenges would not launch interstellar missions. Conversely, a civilization focused on sustainability and well-being might rationally decide such missions aren't worth the cost. Advanced technologies could change the picture. Antimatter propulsion, controlled fusion, suspended animation, nanotechnology, and AI could address energy, longevity, and operational challenges. But each represents a fundamental breakthrough requiring decades or centuries of research, with no guarantee of success. Even then, physics imposes hard limits. Interstellar missions also carry ethical and safety dilemmas. Encounters with extraterrestrial life are unpredictable. The crew, decades away from Earth, would act autonomously, making decisions under extreme constraints with no oversight. High-speed impacts with dust and micrometeoroids pose catastrophic risks. Shielding designs that work in orbit may fail at relativistic speeds. Human needs for stimulation, novelty, and social interaction must be addressed, or mental health and cohesion degrade over decades of confinement. So, are we trapped in our solar system? Not necessarily forever, but plausibly for centuries or millennia. The obstacles are immense, interconnected, and far steeper than the journey from the Wright brothers to Apollo. Yet exploration continues. Probes to planets, moons, and asteroids teach us about resources, planetary formation, life support, and energy systems. Incremental progress builds the foundation for potential interstellar missions, even if realistic crewed missions remain distant. This doesn't mean giving up. The pursuit of advanced propulsion, life support, radiation shielding, and AI has value, with applications closer to home. But interstellar travel is not inevitable. It requires not just engineering but new scientific understanding, new ways of thinking about energy, propulsion, and biology in deep space. The universe is vast beyond imagination. Distances between stars measured in light years make energy demands enormous, hazards constant, and human endurance untested. Costs are astronomical, and benefits uncertain. Yet human curiosity, the drive to explore, and the desire to ensure long-term survival persist. Perhaps we will eventually overcome these forces. Perhaps we will focus on thriving within our solar system while sending small, unmanned probes to distant stars, leaving crude interstellar travel to future generations with better tools. Clarity is essential. The forces limiting interstellar travel are real, fundamental, and indifferent to human desires. Understanding them allows informed decisions about our future in space, whether transcending these limits or flourishing within the bounds of our solar system. The challenges are invisible to everyday intuition, but recognizing them is the first step to either overcoming them or learning to thrive under their constraints.